Welcome to my math teaching online again. So in this video today, I would like to show you one more word problem and how to solve it, which apply the Newton's law of cooling. So let me read the question to you and see how we can solve it. On a hot day, a thermometer is taken outside from an air conditioning room temperature is 20 degrees Celsius. After 1 minute, it reaches 26 degrees Celsius, and after 2 minutes, it reaches 29 degrees Celsius. What is the outdoor temperature? Okay, so let's figure out what is the data given to us. Okay, let me read one more time. Sometimes it doesn't get into my mind when I just read one time. On a hot day, a thermometer is taken outside from an air conditioning room temperature is 20 degrees Celsius. After 1 minute, it reaches 26 degrees Celsius. And after 2 minutes, it reaches 29 degrees Celsius. What is the outdoor temperature? Okay, so this is the question. And given what? T0 equal 20 degrees Celsius. And T1 final equal 26 degrees Celsius. Also, T2 final is 29 degrees Celsius. And the time to reach this is T1 equal 1 minute. And the time to reach up to this temperature T2 equal 2 minutes. Okay, so the time is the same unit, so that's good. We don't have to worry to convert them in the same unit. Now, what is the question? So that's a given. What is the question? The question asks, what is the outdoor temperature? Okay, so basically, the question asks for A, which is air, right? Air temperature. Air temperature. Okay, so let's see how we can do this question. Solution. Now we know that the laws of Newton's law, which is the rate of change of a certain body, whether it was rolling or by heat, temperature, right? It was heated. So in here, we're talking about derivative of dt, temperature, over dt, equal the proportionate rate, right, multiplied with the temperature. So proportionate rate of rho of the body multiplied with that. So that is a basic concept when we first establish the equation. But now we know that this T will become T0 minus air temperature, the difference between the temperature at the beginning and the air temperature. So this iteration this derivative, instead of symbol like that, it will be d t0 minus a over dt equal this. So after we integrate both sides and follow the laws of the natural growth, and we have proven that formula, we will get something like t minus a equal t minus a equal c e kt, adding with okay, let me, so you get something like t 0 minus a e to the kt, adding with kt 0 minus a. Okay, so when we solve for this equation, actually our equation, we move this over, we'll get a adding with t, and remember this represent a function f of x, right? Not just the just one numerical value, but it's the whole function. Or you can write this at t temperature respect to time as well, right? So that will be equal a plus t0 minus a e to the kt. So this become a formula by Newton law of cooling, right? So that's our formula. And we know that if we solve this differential equation, which is we have learned how to solve this before, we just don't want to bother to go through it anymore because we know that this is how it become, right? So now let's follow this formula. So now it's the key, right, to our problem solving. So now let's substitute any number we know in this equation. So we have the first equation is, so our first equation, we have a T1 equal 26. So we know this number, right? We know that number. And A is the one we don't know. Adding with T0, we also know T0. What are our T0? 20 minus A e to the k times t is 1 minute. We know also the time, right? And the next equation we know is 29 degrees equal a plus 20 minus a e to the k times with 2. So in this equation, we have the two equations, right? What is our unknown in here? Our unknown in here is two unknown and two equation. So we'll be able to solve this equation with two unknown, one is a and one is k, right? And the way we solve it, let's see if we can manipulate a little bit. So one, I can make it become 26 minus a equal 20 minus a e k, right? 1k is just k. And question 2, we have 29 minus a equal 20 minus a e to the 2k. So if I look at this number, right? I can see that this root exactly the same like this root. E to the k exactly the same like e to the 2k, except this is 1k and this is 2k. So maybe we can manipulate something about the power and this root in here. We can cancel them. Now, if we want to cancel this and this and this and this, we have to multiply, right? We have to square both sides, and we have to square this as well. Now the purpose we want to square because we want to have 2k look like this, right? So let's do the squaring and see what happens. So we have 26 minus a, all of them square. Let's leave it for now. This one will become square as well, right? If we distribute this into here, and this will become 2k. So now let's copy the number 2 here. We have 29 minus a equal 20 minus a. And this is just power 1, right? And this is e2k. So at this point, we see that we can do something with canceling, right? Because this root on the right-hand side now very much the same. So I'm going to say divide 1 divided by 2, right? If we divide 1 by 2, what do we get? We get, now this root and this root, we cannot divide them because the number is not the same, right? The a is the same, but 26 and 29 obviously is not the same. So on the left side of this equation, nothing you can do about that. So let's copy it down. 26 minus a on of this square equal. Now this we can divide with this because this is power 2 and this is power 1, right? So if we have power 2 divided by power 1, we left with one of them on the top here, right? And we can cancel this with this if we divide them, right? So it means this will disappear. So we only have this. And down here, when we divide, that cancel as well, right? The one on top is the one left over. So now we have 29 minus a equal. Now keep in mind, we divide them, right? So this is like divide. So now this is an equation like this. So I'm going to kick this up here, right? Divide become multiply, and therefore this gone when I kick it up here. So I will bring it up here, 29 minus a. So I bring this up here, divide become multiply to the other side of the equation, and I cancel this, right? When I bring it up here, it disappears. So now I'm going to open the bracket for this. So I have 26 squared minus 2 times a times b, which is 52a, adding with a square will be equal this times this. So let's figure out the number. I'm going to figure out this number as well. Okay, so 26 squared will be equal to 676. And 20 times 29 equal 580. And minus 20a adding with 29a, so it will be 49a, and adding a square. So after you multiply, distribute, this is what you get. Okay. So now after we get this, we know that a square can cancel with a square. The same like you bring it over, a square minus a square is 0, right? So we're going to cancel it. Now, if I bring this over, I will get 676 minus this number, right? Minus 580. So that's for the number. And 676 minus 580, I got 96. Now I'm going to kick this number over here. So when I kick this number over here to the side, minus 52 become positive 52, right? So I'm going to add into 52a. So this is positive, this is negative. Let's subtract. 52 minus 49 equal 3a. So we get whatever here, we bring it over and bring the number over, we get 96, sorry. Yeah, we subtract, we get 96, right? Equal, see equal sign, right? 3a. Now divide both sides by 3, right? We get 32 equal a. So that is our answer for this solution. So now we figure out the air temperature outdoor. So this is the air temperature outdoor. The air temperature outdoor is 32 degrees Celsius. So we figure out the answer by solving the equation. All right, so that's how we answer this question. And I'm going to go over a little bit with you, like a summary at the end, right? Usually. So first, I'm talking about the Newton's law of cooling formula. And so we know that we have the rate of change of the derivative of temperature over respect to time equal proportionate of some constant number of the body material, right? Whatever was heated, whether it's a rod will heat, the steel rod will heat it, or a wooden whatever, right? So K here is stand for that material of the body, time with the temperature. So now we know that the temperature here will be the differences between the initial temperature and the outdoor temperature, right? So it means this derivative will be derivative of the whole thing, the difference between the temperature initial and the outdoor. Now, if we integrate this, it looks very complicated, but if we substitute t minus a here, it's just the letter t or y over dt. And we went through the whole thing about solving the equation, something like dy over dt equal ky, right? So if we treat this y, it's the same like this is like a y, and this is like a y, and we solve, we end up eventually, we ended up with our y equation is something like c e to the kt. Remember, we went through that, right? So now on what we do is substitute y as a t minus a, right? This is the difference between the initial temperature and air, the temperature of the air, right? Air temperature. So we know this is t minus a equal this, the same like the c here. If we put initial T0, the time at the beginning when it hasn't changed the temperature yet, then the K here becomes 0, and the C will be equal T0 minus A. So we substitute C by this root T0 minus A for C, right? And this is how we get. So now we will find the function f of x, which is this one, right? Which is the same like this one, right? We move this over, we get this formula. So this is how our formula look like. And this is, we call it Newton's law of cooling formula. So now we can use this formula to solve any application problem easily, because this is the tools the mathematicians develop for us to use. So they invent formula, they invent the equation, they solve it, and now all what we do is accept this is true, follow it, learn to understand the formula, how it derived from, how can we have this formula, understand the meaning of it, and use it, right? So when I use this equation and answer this, so then after we put in the number, substitute any letter in here, we know, right? Based on this information, right? We know the 26 is the final T1 equal the air temperature adding with T0 20 minus A, we get the first equation. Then the same for the second one, we get this. Equate them, divide equation 1, equation 2. We notice we have to square both sides of this equation to be able to cancel the 2k with the 2k here, and the 20 minus a power 2 with the 20 minus a power 1 here, because we know that nothing we can do about this and this, but we can manipulate this, divide by this. So that's why we square both sides for the first equation, so that we can get 2k, so we can cancel some of the unknown number we don't know, and the less unknown letter we eliminate to become the least, then maybe we can solve it. That's how we solve an equation. We try to eliminate the unknown letter as much as we can whenever we see the opportunity. So we see the opportunity here, this look like this. So all what we do is square this to get 2k the same, so we can cancel. But once we square this number, we have to square the whole thing on the right-hand side and the left-hand side as well. That's the rule of equation. And that's why we did this. Okay, so after we divide 1 divided by 2, we cancel this, and this cancel with that, we left with this for the first equation and divide this. So all what we do is kick this number down here, up here. When you transfer one thing from the left side to the right side, from the original, you have to change the operation. Divide become multiply, and you cancel it. And this is what we get. So at the end, we get the answer. The air temperature is 32 degrees. So I hope that after I summarize the second time for you, you get it, you understand it better and get it more easily. So that's it for the video now today. Thank you for watching, and bye for now. Stay tuned for our next video coming soon. Thanks for watching. Good night, everyone.